Okay, so we're starting chapter 14 now, and we're going to spend a solid chunk of time here. There's a lot to cover in chapter 14, a total of 8 sections, and this is where we really start getting into the multivariable part of this course, multivariable calculus. What we need to do before we can really do any calculus is start familiarizing ourselves with these things that we call multivariable functions, or functions of several variables. That's the name of the section. Let's start with the definition of a function of 2 variables, but then we're going to just sort of generalize this to a function of several variables. So if you have a function f and it's a function of 2 variables, we think of that as a rule that assigns to each ordered pair of real numbers x, y in a set that we're going to call the domain of that function, some third value, some scalar value that we call f of x, y. The set D, like that's mentioned here, is what we call the domain of f, and the range is the set of all values that f takes on. So it's similar to domain and range for functions of a single variable, what you've seen before. This is just a set builder notation for the range of this function. So as is often the case, anytime you encounter a definition that's kind of written in formal mathematical language, it can become difficult to really identify what it's talking about until you see some examples. And we're going to look at some examples in a little bit. But the key thing here is that a function of 2 variables is a function that takes 2 different inputs. These, the x and the y here, are 2 independent variables, and they both get plugged into a function, and a single output is produced from that. So before we get into working with these functions of 2 variables, getting hands-on with them, I want to look at some examples, and I want to generalize this as well, because again, this is a function of 2 variables, but we can talk about functions of any number of variables. So for example, a function of 3 variables would look like f of x, y, z. X, y, and z in that case would be thought of as independent variables, all of which could receive, represent some input that you plug in, and then a 4th number comes out as an output. Or we could talk about a function of n variables for any number n. So here's a few examples of sort of real-world functions of several variables that are worth considering. The first 3 here, these 3, are all kind of the same idea. They're all representing temperature of some location on Earth. So, for example, if you consider the geographic coordinates of a point on Earth as an ordered pair, x, y, so you can think of it as, latitude and longitude, then we can denote the temperature at those coordinates as a function of the coordinates themselves, t of x and y. Notice the temperature depends not only on the latitude, but also the longitude, which go together to identify a point on the surface of the Earth. We can add another variable into that same function if we want to consider the elevation at a particular point on the Earth. So as you kind of go up in elevation or down in elevation, but stay fixed at some specific point on Earth, the temperature can change. So elevation is worth factoring into that temperature function as well. So again, geographic coordinates x, y, some location on Earth. If we let z denote the elevation at that point that we want to measure a temperature at, then t of x, y, z is a function of 3 variables. The output of this function is temperature, but the input is latitude, longitude, and elevation. Finally, another function that deals with the same concept but includes a 4th variable. If we want to measure the temperature at a particular point on the surface of the Earth at a given elevation z, and also at a specific time. So we know that temperature can vary depending on time of day that you measure it. So time is a variable that influences that temperature as well. We may want to include that in our function and make the same function that we've dealt with in these previous 2 examples a function of 4 variables: latitude, longitude, elevation, and time at which the temperature is recorded. All 4 of those variables would be inputs for this function, and the output would be the temperature reading that we get. So moving away from this one, kind of specific example that we've sort of elaborated on, but still dealing with the world of temperature, I want to talk about Another example that you study if you ever take a course in partial differential equations. We'll actually talk a little bit about partial differential equations later in this chapter, and we may even encounter this exact example again. But this is something that we study in that class, and from it we get something called the heat conduction equation. The idea here is that we have a thin metal rod of length L. So you see how it goes from 0 to L here. And by thin, we want to interpret it as a one-dimensional object, a one-dimensional line segment. The only reason for that is because we want to simplify the number of variables that we need to consider for this. So if you take this thin metal rod and apply a heat source to it somewhere on the rod is going to heat up. Let's denote that temperature by lowercase u. That's typically how the heat conduction equation deals with temperature. The label that they use is u, typically. And let's suppose that we want to make u the output of our function. So we want to get temperature readings on this thin metal rod. What variables influence the temperature? Well, if the heat source, for example, is applied not on the entire rod uniformly, but maybe at like one end point of the rod. You can see from the color here, this part of the rod is red, and then it kind of fades into cooler colors as we get towards L. So maybe the heat source is being applied here at 0. That implies that the heat in the rod, the temperature of the rod, is going to vary according to where we take that measurement on the rod. Different points on the rod will have different temperatures. Parts will be hotter, other parts will be cooler. So if we let x denote the point on the rod, because we're thinking of this as lying on the x-axis, x would be one of the variables that needs to be considered. However, kind of like in the previous example, time is also a factor. Because again, if you take this heat source and apply it to this rod here at 0, the points over here are not going to be as hot as the points over here, but as time passes, the rod will continue to get warmer and warmer, raising up to the level of that heat source. And so the temperature at all of these points will be changing as time passes, which means if we let t denote time, then t is another variable that we have to consider for the temperature along different points of this rod. So u of xt, it's a function of two variables denoting the heat of that rod at particular points and particular times. Here's kind of a more general one with n variables instead of 2, 3, or 4 specifically. Suppose you have a retail chain with n stores in a particular city. Could be Starbucks or something like that. It's more of a food service type of thing, but you know, it's just some big franchise or something with n stores in a particular city. And suppose that the stores generate revenue, as they should if they're going to stay in business. And let's suppose that the revenue generated by each store in a given week is given by these values here, x1, x2, all the way through xn. These are variables, and they're all independent of each other. We're going to assume independence anyway. So, you know, the Starbucks over on this corner is going to earn, over here, is going to earn, you know, whatever revenue it earns that week. And over here, this Starbucks is probably going to, you know, earn a different amount of revenue, and these two things are independent of each other. So if we want to determine the total revenue generated by all of those stores over the course of a particular week, that's a function of all n of these variables. We can call that a revenue function, r of x1, x2, all the way through xn. And this one we can actually come up with a rule for. It's just the sum of all those individual revenues accumulated during that week. Next example, last example of this type that I want to look at is one that your book goes into a lot of detail on. I'm just going to mention it here, but you can take a look at where this came from in your book. This is another one kind of dealing with economics. It's the Cobb Douglas production formula. This was or function, sorry. This is a function that was derived back, I believe it was the 1920s, based on a study that was done by these two researchers. They collected a lot of data, and then they formed a mathematical model from that. But the idea is they want to look at the total economic output of a particular economy, and they want to consider it as a function of two variables. labor and capital invested in that economy. Labor is measured in person hours per year. Capital invested, capital is money, but it's not just money. It considers the value of all the assets that are used, machinery, equipment, and stuff like that. So this is a simplified model because the economy, any given economy is an extremely complex system, and there's several more variables that go into determining economic output. This was just intended to be a simplified model. But the function they came up with was that the economic output P, as a function of labor and in capital invested, is given by this function right here, 1.01 L to the 0.75, K to the 0.25. So I would suggest going and taking a look at that section in your book that talks about this to kind of familiarize yourself with that function. It's just a good example of a multivariable function. So let's actually do something hands-on with this. Here's a function of two variables. F of x, y equals square root of 4 minus x squared minus y squared over x squared plus y squared. We want to do a couple of things with this. First, we want to evaluate f of 1.0. So that's easy enough to do. The key to remember here is that in a two-variable function, you have an x and a y. So you plug the x into the x's, the y into the y's. This is equal to the square root of 4 minus 1 squared minus 0 squared over 1 squared plus 0 squared. This would be equal to root 3. Okay, pretty easy to see that. Next thing it asks us to do is to determine and sketch the domain of f. Remember, the domain is the set of all ordered pairs, x, y, that can be plugged into this function. And as is the case in like an algebra class, when you're trying to determine the domain of a function, oftentimes it's helpful to look at what things you can't plug in first. So starting with my numerator, I have this radical here. And this radical, we know the radicand cannot be negative. We need 4 minus x squared minus y squared to be a non-negative number in order to take that square root. So 4 minus x squared minus y squared has to be greater than or equal to 0. Okay? But this is the same thing. If I kind of move some things around, as saying x squared plus y squared is less than or equal to 4. Okay, now that's a restriction on x and y, but if we think about what that looks like graphically, because there's two variables now, this domain can be graphed not on a number line but in the plane, in the Cartesian plane. This would look like a disk centered at the origin of radius 2. So we're asked to sketch the domain. We're going to keep that in mind. But there's one more restriction to pay attention to here. Down below, I have x squared plus y squared in my denominator. And we know that we can't divide by 0. So that means that x squared plus y squared cannot equal 0. Now, because both of these terms are being squared, as long as x and y are not both 0, this will always come out positive, right? Even if one of them is 0 but the other is not, 0 plus any non-zero number squared will come out to a positive number. So that's not a concern. However, if both x and y are equal to 0, then 0 squared plus 0 squared would equal 0, and we can't have that. So this implies that xy cannot equal 0, 0. Okay? So let's first determine how we write this as a set. What is the domain of this function? Well, D is equal to the set of all x, y such that x squared plus y squared is less than or equal to 4, and x, y is not equal to 0, 0. Okay? That's a valid way to write that. Notice it's the same things that I stated here, but kind of in that set builder notation. Now, how do we sketch this? Well, like I said before, this inequality, we know the region that it's describing is a disk of radius 2 centered at the origin. So that would be something like this, 2, 2. However, when we are talking about a disk as opposed to a circle, we would shade this in to indicate that all the points interior to that circle are included in the domain. Except we want to be careful because one of the points in the circle shouldn't be included, the origin in particular. So I can put an open circle around the origin to indicate that that doesn't belong to our domain there. So that would be the domain D. I'll label it D. Sometimes this is called a punctured disk because it has a hole in the middle. Okay, let's move on. So we want to look at how you take a function of two variables. We're going to focus on functions of two variables at first and sketch a graph. You know that if you want to sketch a function of one variable, f of x, then we think of f of x as meaning the same thing as the variable y. That way we get x values and y values corresponding to that function, ordered pairs corresponding to that function, and then we can graph those in the form of a curve typically. The difference here, if you're talking about a function of two variables, x and y, both of those variables go together into these ordered pairs, which are points in your domain. So the domain of a two-variable function is a subset of the xy plane. Here, for example, if this is the function that we're looking at, f of x, the domain of this function might be this little yellow region down here, D. What we do is we pick points in the xy plane, plug them into the function, and then that output we interpret as z. We think of that as the point, or the value z, and then we use that z with our x and our y to create ordered triples, putting that point somewhere in 3 space. So in this case, the domain D consists of all the points that we can plug into f of xy. Once we plug them in, the values that we get from that go together to create ordered triples, producing this surface here, which we're calling S. Okay, so the domain lives down here, but the actual graph of f of xy in this case looks like this blue surface. Let's try doing one of these by hand. I want to sketch the graph of f of xy equals 6 minus 2x minus 3y. So a good way to do this is to replace the f of xy with a z. Because again, that's the idea. We want to think of that as the z value of the points that we're graphing. 6 minus 2x minus 3y. Let's write this differently. This is the same thing as 2x plus 3y plus z equals 6. Okay. Looking at this, I recognize this as the equation of a plane from chapter 12. Pretty clearly the equation of a plane. And in chapter 12, oftentimes when we were asked to graph a plane, we focused only on the first octant because it's difficult to see where that plane is otherwise. So x, y, z. And we can use this intercept method in order to do this. If I want to determine where this plane intersects the x-axis, that's where both z and y are equal to 0. So I plug zeros in for y and z, giving me 2x equals 6 or x equals 3. 1, 2, 3. The graph will have an intercept there. Same thing here. If I want to find the y-intercept, plug in zeros for x and z, giving me 3y equals 6 or y equals 2. 1, 2. Okay, and then same idea, plug in zeros for x and y, z equals 6. 1, 2, 3, 4, 5, 6. Up there. It's a plane, but its intersection, or sorry, it's the part of the plane in the first octant would look kind of triangular like that. So there's our surface. Okay, there's the graph of our function. All right. So oftentimes we like to visualize the graph of a function of two variables in a different way. So here we've looked at a couple of examples. This is just sort of a general example. The graph looks like a surface. You need 3 dimensions to represent that surface. Here's another example. I needed 3 dimensions to represent that triangular piece of the plane that I wanted to graph. But it's actually possible to visualize a function of 2 variables in 2-dimensional space. And we do that using a special kind of projection. So take this, for example, right here. This surface shown here looks kind of like a bump. You know, if you were to take some horizontal planes of the form z equals k, so that they would be parallel to the xy axis, and use them to intersect this this surface here. Notice that those intersections in this case would look like circles at different elevations, right? So if you take those circles, or they can look like something completely different in a different example, those intersections, and then project them down into the xy plane like we're seeing here, then you get what are called level curves. So in this example, our function f of xy has different elevations that you can consider on this surface, but again, if for example, you want to look at the set of all points on this surface that have a z of 30, you know, that might correspond to this circle right here. We can project that down to the xy plane and then just say, you know, this is the circle where f of xy is equal to 30. So it's a useful way of sort of thinking about the graph of a function of two variables without needing three-dimensional space. So let's take a look at an example. Before we do that, the graph that you're seeing down here in the xy plane of all these circles, in this case, we call this a contour map. So a contour map is a graph consisting of several level curves. All right, so we're going to try and sketch one of these. We're actually asked to do two things. We want to sketch the graph of this function, f of xy equals square root of 16 minus x squared minus y squared. And then we want to sketch a contour map for f. So the graph itself will be three-dimensional. The contour map will be two-dimensional. And again, kind of like we did in the example with the plane, we want to set f of xy equal to z. Z equals the square root of 16 minus x squared minus y squared. Okay, now if I were to square both sides, z squared is equal to 16 minus x squared minus y squared, or x squared plus y squared plus z squared equals 16. There's one thing we do need to be careful about, though, because looking at this initially makes you think this is a sphere centered at the origin of radius 4. That's the equation for a sphere from chapter 12. But that wouldn't really work because, again, if we only had this equation, I'd be allowed to plug negative values in for z, because then I could just square them, it becomes positive, and then, you know, they could be parts of the solutions to this equation. Up here, though, z is set equal to the square root of something. This implies that z can't be negative. So we need to include this condition when we're thinking about the graph of this thing. Z has to be non-negative. What that means is that instead of looking at a sphere of radius 4, we're actually looking at a hemisphere of radius 4. So 4, 4, 4, kind of this circle here. Okay, doesn't look great, but that's like the top half of the sphere that this equation would represent without this condition. Okay, so the next thing I want to do is think about what a contour map for this function might look like. And remember, we're taking this hemisphere and we're slicing it with planes of the form, you know, z equals k for some constant. So basically all that amounts to is looking at f of xy equals k for a few different values of k. Let's say k equals 0, 1, 2, 3, and 4. We should get a good, there we go. We should get a good contour map out of that. So I can see just kind of from my graph that those level curves should look like circles. But I want to be a little bit more accurate with them. So again, this contour map is going to live in two-dimensional space. There's my x and my y. And let's think about what different values of k might correspond to here. Again, remember, f of xy is the same thing as z. So I can go down even to this last equation here and plug these different values in. For example, if I plug z equals 0 into this, then this equation reduces to x squared plus y squared equals 16. That's a circle of radius 4. So we got 4, 4, negative 4, negative 4. Like that. Okay. Now, what we typically want to do is put some label on here to indicate what value we were using for z, or we're actually going to call them k here. So this is where k was equal to 0. What if k is equal to 1? Let me call this k instead of z. K equals 1. Well, now, if I plug 1 in, remember z is equal to k. We're using constants for z here. If I plug a 1 in, I get x squared plus y squared equals 15. 1, 2, let's get a little bit more going here. That. Okay, so this would be a circle centered at the origin with a radius of square root of 15. That's going to be pretty close to the other circle out here. So it's going to do something like this. Okay, this would be where k is equal to 1. And then if we do some other values, k equals 2, what happens to this? Well, in this case, if I plug a 2 in, 2 squared is 4, subtract that from both sides, I get x squared plus y squared equals 12. Okay, that's a circle centered at the origin with a radius of root 12. Now I know root 12 is a little bit bigger than 3, because 3 is equal to 9 squared. So root 12 would be a little bit bigger than 3 because of that. So I'm going to put that one maybe here. This is where it's helpful if you're good at sketching circles. Mine's already not looking great, but just trying to give you a general idea. So this is what I would call k equals 2 there. And then we could do a couple more. K equals 3. If I plug a 3 in here, x squared plus y squared plus 9 is what I'll get, equals 16. Subtract 9 from both sides, and I get 7. X squared plus y squared equals 7. Okay. So square root of 7 is a little bit less than 3. That means I would be looking right around here. Okay, so that would be like k equals 3. And then maybe one more. K equals 4. So if I plug 4 in for x squared plus for z right here, then 4 squared is 16. Subtracting that from both sides gives me x squared plus y squared equals 0. As we saw before in that question where we were looking at the domain of a function, this can only equal 0 if x and y are both equal to 0. So that wouldn't even look like a curve. That would just look like a point here at the origin. K equals 4. Notice how quickly it shrunk down from 3 to 4 there. Okay, so this thing, even though it's not terribly well drawn, this is what we would call a contour map for the graph of this function right here. That's all the time I have for this video. We'll finish this off in the next one.